on what we've been talking about. So it looks like more and more of the same stuff. We're going to think overall, put it in the corner, about what's known as an acetal. We're going to think about how we can use these acetals as protecting groups. So we've already seen this silo protecting group. It's a weird G, but we'll just go with it. We're going to see the sulfur equivalent, which is known as a thioacetal. And then last, for next week, carbohydrates. This is a bad idea, writing it so close to the edge. I bet we can't even see that. I'm going to basically just do the same thing, it looks like. Carbohydrates. Sugars. That would be easy, right? So let's first of all think about this acetal formation. What is that? And now let's take our ketone. In this case, we'll just use acetone again because it's an easy example. If we're going to take acetone and react it with methanol, and say 2 equivalents of methanol, that's what that 2 is supposed to be. So it's 2 equivalents. Or you could also think about it in terms of moles. Okay, yes, so the video's about increasing those neural networks. Excellent. It's very well thought out. So I will keep it up. I will do the video. I just can't watch it because I don't know if anyone else has experienced this too, but when you hear yourself speaking on something, you sound so much different than you think you sound, is the thing. So I know it's a little bit just, you got to get over it. But that's always one of those things. And then you realize the words that you say that are the ones you use to buy time and things like that, whether it be basically or essentially or and those types of things. But if it helps, we will have the videos, and so I will do that. For this reaction, now we're going to use 2 equivalents, or you can think about it as 2 moles. So we're going to take 2 moles of methanol with 1 mole of acetone. We have a little bit of acid. So this is a generic acid, H+, like we've seen with H3O+. And we end up getting this species here where it looks like we've added the 2 methanols to what was the ketone that we started with. This species here that has the carbon connected to 2 ethers is known as an acetal, is the name of that group. So now let's think about what sort of a mechanism could end up forming this species. And this is a fundamental mechanism, and this is the one I went through on that video, so I think it's important, so we'll go through it together here and see how it develops. So as mentioned, I think it was yesterday, from here on out, when we see a carbonyl-containing compound in the presence of acid, the first thing we want to do is to protonate the carbonyl group. So we have 2 lone pairs of electrons here. Our acid is going to be used to protonate this carbonyl group. All of these steps actually are reversible, and this is important. And what this does is it makes now this species much more electrophilic. So that now our weak nucleophile, which before was water, so this looks just like what we did with water, but now it's methanol, can go ahead and attack. And I guess I'll put the arrows at the bottom to save some space. So I'm going to put the OH over here, and I'll put the methanol here. So now we have OCH3, and then we have this hydrogen. And that's positively charged. Now, what we're going to do is take off the proton. So we're going to deprotonate. You can use water. OCH3 here, H3O+. And next we're going to actually now protonate. Electrons are different colors, but okay. Protonate this. We'll go down. This is all the same. And this is now a key step. So what we've ended up doing here is by protonating this hydroxyl group here in the top part, we've turned a poor leaving group, if this were to leave, into a really good leaving group. Now, if this carbon-oxygen bond breaks, this is going to leave us water. So that's going to be a good leaving group. We need to have something to act as a nucleophile. Now, a common tendency is to have, say, something nucleophilically attack here and kick out the water in an SN2-like reaction, but that will not happen. This carbon is very sterically hindered. We have these methyl groups around, we have this OCH3 around, so it's going to be very sterically hindered for a nucleophile to attack. However, we have these two lone pairs of electrons in this oxygen right here, so what they're going to do is kick out our leaving group. So come in here, kick out our leaving group, and this is also favorable because it's going to reform the carbonyl group. So we have this. We've lost water. Put water down here. And now what we can do is have another equivalent of methanol attack. And let's just put the original methanol over here. And one more step is we need to take off that proton to generate our acetal. So there's our acetal. Sorry, I should put this one in there too. Plus. So we regenerated our acid. So this looks like a relatively lengthy mechanism, and indeed it is. However, this is key to a variety of reactions that we'll see. And if you look at the different components, then hopefully it makes sense. We have a carbonyl group in the presence of acid, so we're going to protonate the carbonyl group, making it much more electrophilic. Our weak nucleophile methanol attacks. And then we have a series of proton transfers. There's a tendency to try to draw this all in one step, just having this proton jump over here. That's probably not the way it occurs. I'm not drawing it in these multiple steps just because I like to draw things, but this is a better representation of it. Water is going to take a proton off, and then this group is going to get protonated. That turns this hydroxyl group from a bad leaving group to a good leaving group, which then can get expelled by reforming the carbonyl group, like these lone pair of electrons on this oxygen, kicking out water. And now in the next step, another methanol can attack. And then that looks just like, I guess you can't see me pointing, this step here, I'm trying to highlight, looks like this step up here on the left, same idea. Methanol attacks, forms a new carbon-oxygen bond, and then a deprotonation. So a very common mechanism. A few more points about this is that all of these steps are reversible. This is important because we're going to use this as a protecting group. One of the things I would encourage you to do as a subtle hint to something that one might be seeing next Thursday is to draw the reaction in reverse. Think about the arrows, how the arrows would go in reverse, because this is a reversible reaction. A couple of other points, just to reiterate again, that one of the most common things I see, I'll write it here, but hopefully we'll make it stand out. Should we try that magenta again? There's a tendency to try to have methanol just come in here and kick out this water, but that's not going to happen. It's not SN2. That's the most common error I see. And I know it's maybe a little picky, but it's thinking about the reactivity. This carbon is quite sterically hindered, so there's not going to be an SN2 attack. You have to kick out the leaving group from this adjacent oxygen and then have the nucleophile attack. One last issue with this too is one might ask, why doesn't just water attack here instead of the methanol? And it does. It happens at times, because that's going to go back over to this product that we have here. So that's why all of these steps are also reversible. The way you would do this reaction is probably you'd have a lot more than just two equivalents of methanol. So that in the actual reaction flask, methanol bumps into this ketone, this protonated ketone. Sometimes water bumps into it. It goes back and forth, but there'll be a lot more methanol around, so the reaction will go forward. While we're harping on this, one last thing too is that when we draw this, say a water molecule taking this proton off, and then showing the proton getting put on. In reality, it's not going to be the same water molecule. There's water molecules and methanol all bumping into each other, transferring protons. So protons are going to get transferred all over the place. The acid that we have in here could protonate the methanol. That methanol is going to then protonate the water molecule, going back and forth. And so there's all sorts of other reactions going on behind the scenes, even though we write this really linear pattern. Let's go scroll up a bit. To help reinforce this mechanism, let's draw actually the mechanism for a cyclic acetal. And we'll see it's the same thing. So we could take